Hi, I'm Bob. Welcome back to the tutorial on how to solve the exercises in the textbook Microeconomics Theory and Applications with Calculus, the 5th edition. We will continue to address the static game problems in chapter 13 of game theory. Here's exercise 1.11. Suppose that Panasonic and LG are the only two firms that can produce a new type of holographic TV. The payoff matrix shows the firms' payoffs. In part A, if both firms move simultaneously, does either firm have a dominant strategy? Explain. In part B, what are the Nash equilibria given that both firms move simultaneously? It is a static game of complete information. We draw the payoff matrix for the two players. The first number in each cell is LG's profit, and the second number is Panasonic's profit. We use the best response approach to find the Nash equilibrium. We first consider LG's best response to each of its rivals' actions. Suppose Panasonic chooses to enter the market. LG gets minus 40 if it enters the market. It gets 0 if it stays out of the market. LG's best response is to stay out of the market. We underline its payoff 0. Suppose Panasonic chooses not to enter the market. LG gets 250 if it enters the market, but 0 if not. LG's best response is to enter the market. We underline its payoff of 250. LG does not have a dominant strategy. Next, we figure out Panasonic's strategy. Given that LG enters the market, Panasonic's best response is not to enter the market because it brings a higher profit. Given that LG does not enter the market, Panasonic's best response is to enter the market. We underline the corresponding payoffs. Panasonic does not have a dominant strategy either. Finally, we circle the two cells with both payoffs underlined. There are two pure strategy Nash equilibria. In part C, the South Korean government commits to pay LG a lump sum subsidy of $50 million if it enters the market. What is the Nash equilibrium? The subsidy changes some payoffs and therefore may change the Nash equilibrium. Two numbers are different now. If LG enters the market, its profit will increase by 50. We will use the best response approach to find the new Nash equilibrium. Given that Panasonic chooses to enter the market, LG gets 10 if it enters the market, but 0 if not. LG's best response is to enter the market. Given that Panasonic does not enter the market, LG's best response is still to enter the market because it brings a profit of 300 instead of 0 if it does not enter the market. LG has a dominant strategy, that is, to enter the market no matter what Panasonic chooses. Knowing that LG will always choose to enter the market, Panasonic's best response is to stay out of the market. The pure strategy Nash equilibrium is that LG enters the market and Panasonic does not. Let's go to exercise 1.12. Two guys engage in the game of chicken. They drive toward each other in the middle of a road. As they approach the impact point, each has the option of continuing to drive down the middle of the road or to swerve. Both believe that if only one driver swerves, that driver loses face and the other gains in self-esteem. If neither swerves, they are maimed or killed. If both swerve, neither is harmed. So the payoff matrix for the two drivers engaged in this game of chicken determine the Nash equilibria for this game. We can draw the payoff matrix for the game of chicken. The first number in each cell is player 1's payoff, and the second number is player 2's payoff. We use the best response approach to find the pure strategy Nash equilibrium. We first consider player 1's strategy. Given that player 2 chooses to drive down the row, player 1 gets -10 if he drives straight and gets killed. He gets 0 if he swerves. Player 1's best response is to swerve. We underlie his payoff 0. Given that player 2 swerves, player 1's best response is to drive down the row because it brings a higher payoff. We underlie his payoff 2. Next, we figure out player 2's strategy. Suppose player 1 continues to drive down the row. Player 2 gets -10 if he also drives straight and gets killed. He gets 0 if he swerves. Player 2's best response is to swerve. We underlie his payoff 0. Suppose player 1 chooses to swerve. Player 2's best response is to drive down the row because it gives him a higher payoff. We underlie his payoff 2. Finally, we circle the cells with both payoffs underlined. There were two pure strategy Nash equilibria. There is a mixed strategy Nash equilibrium of the game. We assume that player 1 drives down the row with a probability of beta. Player 2's expected payoffs for each of his strategies can be calculated. Player 2 should be indifferent between his two strategies. We can obtain beta, which equals 1/11. Similarly, we can compute alpha, the probability at which player 2 drives straight. It also equals 1/11. The mixed strategy Nash equilibrium is that player 1 drives straight with a probability of 1/11 and swerves with a probability of 10/11. Player 2 drives straight with the same probability. Let's go to exercise 1.13. Modify the payoff matrix in the game of chicken in exercise 1.12. So that the payoff is -2 if neither driver swerves. How does the equilibrium change? We still use the best response approach to find the pure strategy Nash equilibrium. the two Nash equilibria are unchanged. We then use the same reasoning as in exercise 1.12 to find the mixed strategy Nash equilibrium. The expected payoffs for the players' two strategies should be equal to each other. Otherwise, the player will choose to drive straight or swerve with certainty, and the result becomes pure strategy Nash equilibrium. The mixed strategy Nash equilibrium is that player 1 drives straight with a probability of 1/3 and swerves with a probability of 2/3. Player 2 drives straight with the same probability. The mixed strategy Nash equilibrium changes because some payoffs are different from the old ones. The damage from the head-on collision becomes less severe. That is why the probability of driving straight ahead becomes higher. Let's solve exercise 1.14. In this game, Wesley decides whether to put the poisoned Y on the table close to Vicini or close to himself. Then, with Wesley's back turned so that he cannot observe Vicini's move, Vicini decides whether to switch the two glasses. Assume the two simultaneously drink all the wine in their respective glasses. Assume also that each player's payoff from drinking the poisoned wine is -3 and the payoff from drinking the safe wine is +1. Write the payoff matrix for this simultaneous move game. Specify the possible Nash equilibria. Is there a pure strategy Nash equilibrium? Is there a mixed strategy Nash equilibrium? The two players cannot observe each other's actions, so it is a static game, although they move sequentially. We can write the payoff matrix as follows. Wesley has two strategies: to put the poisoned Y close to Vicini or to put the poisoned Y close to himself. Vicini has two strategies: to switch the Y or not. The first number in each cell is Wesley's payoff and the second number is Vicini's payoff. We use the best response approach to find the pure strategy Nash equilibrium. We first consider Vicini's strategy. Suppose that Wesley puts the poisoned Y close to Vicini. Vicini gets 1 if he switches the wine, and he gets -3 if not. His best response is to switch the wine. We underline his payoff 1. Suppose Wesley puts the poisoned Y close to himself. In this case, Vicini's best response is not to switch the wine because it brings a payoff of 1 instead of getting poisoned. We underline his payoff 1. Next, we figure out Wesley's strategy. Given that Vicini will switch the wine, Wesley's best response is to put the poisoned Y close to himself and get a payoff of 1 instead of -3. Given that Vicini will not switch the wine, Wesley's best response is to put the poisoned Y close to Vicini and get a positive payoff. We underline the corresponding payoffs. We cannot find any cell with both payoffs underlined. There is no pure strategy Nash equilibrium in the game. We will find a mixed strategy Nash equilibrium. Suppose Wesley puts the poisoned wine close to Vicini with a probability of alpha. We calculate Vicini's expected payoffs for each of his choices. If he switches the wine, his expected payoff equals the payoff in each possible outcome times the probability of that outcome. It is a function of alpha. His expected payoff for not switching the Y is also a function of alpha. Vizzini should be indifferent between his two strategies. That is, the two expected payoffs should be the same. Otherwise, he will choose one of his strategies with certainty. For example, if the expected payoff for switching the Y is higher, then he will switch the Y with certainty. Given that, his rival will choose to put the poisoned Y close to himself. Knowing that, Vizzini will change his strategy. The game will not have an equilibrium. Only when Vizzini is indifferent between the two strategies can the game have an equilibrium. The equation leads to the solution of alpha, the probability at which Wesley puts the poisoned Y close to Vizzini, which is 0.5. The same reasoning applies to the other player. We can find beta, the probability at which Vizzini switches the Y, which is also 0.5. Therefore, the mixed strategy Nash equilibrium is that Wesley puts the poisoned Y close to Vizzini with a probability of 0.5, and Vizzini switches the Y with a probability of 0.5. Let's find the answer to exercise 1.15. Suppose that you and a friend play a matching pennies game in which each of you uncovers a penny. If both pennies show heads or both show tails, you keep both. If one shows heads and the other shows tails, your friend keeps them. Show the payoff matrix. What, if any, is the pure strategy Nash equilibrium to this game? Is there a mixed strategy Nash equilibrium? If so, what is it? The payoff matrix is as follows. Player 1 wins if two pennies match. Player 2 wins if two pennies do not match. The player who wins gets a payoff of 1. The player who loses gets 0. We use the best response approach to find the pure strategy Nash equilibrium. We first consider player 1's response. Suppose player 2 chooses head. Player 1 gets 1 if she chooses head and gets 0 if she chooses tail. Her best response is head, and we underlie the corresponding payoff of 1. Suppose player 2 chooses tail. Player 1 gets 0 if choosing head, but 1 if choosing tail. Her best response is tail, and we underlie her payoff of 1. Next, we consider player 2's choices. Given that player 1 uses head, player 2's best response is to choose tail because it brings a payoff of 1 instead of 0. Given that player 1 uses tail, player 2's best response is head. We underline the corresponding payoffs. We cannot find any cell with both payoffs underlined. There is no pure strategy Nash equilibrium in the game. We will find the mixed strategy Nash equilibrium of the game. Assume that player 1 uses head with a probability of alpha and tail with a probability of 1 minus alpha. We calculate player 2's expected payoffs for each of her strategies. Player 2 should be indifferent between her two strategies. We can obtain alpha, the probability at which player 1 chooses head, which is 0.5. The same reasoning applies to the other player. We can obtain beta, the probability at which player 2 chooses head, which is also 0.5. Or we can get the result by symmetry. Therefore, the mixed strategy Nash equilibrium is that player 1 chooses head with a probability of 0.5 and player 2 also chooses head with a probability of 0.5. Thank you so much for watching this video and solving the exercises with me today. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.